This is Ben with Measure Quick, and with me today is Jim Bergmann and Bill Spohn, two young fellas who claim to know a thing or two about HVAC. Thanks for being here, guys.
Thanks for inviting me.
Yeah, thank you. I'm glad I paid you to be here.
How serendipitous that we all ended up being in the same place at the same time.
Yeah, miracle.
So we're getting into the fall shoulder season. It means that HVAC professionals may have some time to take a breath and learn a few things about smart tools and heat pumps. Today, I'll be throwing a couple questions at Jim and Bill about cold climate heat pumps, commissioning, and the standard of care that HVAC contractors should be offering to homeowners. So, the Inflation Reduction Act is predicted to create a lot of demand for heat pumps. But how is this actually going to play out for a typical contractor, at least in your opinion?
I think the contractor has to have confidence that they know they're not going to be creating trouble instead of opportunity. And the way most people gain confidence in a lot of things they do is by reps, by repeating activities, getting better at it as they go. A lot of people use guides or systems or programs to help them do that. Think in your financial life, physical life, family life, sometimes even your religious life, you do this. You repeat things, you get better at them, you use guides or things like that. So I think how it's going to affect contractors, those that shun guides, those that shun experimenting with it and learning from it are going to have more trouble and perhaps abandon it altogether.
Because that leads me into the next question, which is, if you even heard Jim say this before, there's only a 1-part difference between a heat pump and an AC system.
Sure.
So if it's all about reps, I should already know what I'm doing if I know how to install a AC system, right?
You would think. My results varied.
Let's just hear that story a little bit first.
So contracted with a builder to build a new home, our first and our last new home. They were using modular construction, which is really neat, building in a factory. But they decided to use their own general manager, versatile jack of all trades guy, to install the heat pump here. And we had designed the house with a good blower door score, 790 CFM 50. With southern exposure, lots of windows facing south. We figured we have some real advantages here, triple pane windows that are going to make us through the winter. And had actually Michael Hausch and Russ King both do load calcs and arrived at a 2-ton air source heat pump. But the jack of all trades installed the heat pump, saying in advance, saying, I've installed a couple of these before, but I install mostly ACs and furnaces. As Jim knows, he was intimately involved later in the next chapter. But I offered the guy all the tools, all the resources, links to videos, downloads and guides, just everything to say, I want you to do the best job you can. And here, I'm going to help you. I was trying to be the guide or the coach and give him information. He decided to shun that information. I asked to be told when he was doing the install. He told me the day after it was done. It worked in air conditioning mode from July when he installed it until we switched to heating mode in November. I installed an energy monitor after about a month and found that the electrical usage was way higher than anticipated. And that's when I called Jim. Because I confirmed it by using temperature probes at various points in the system and determined the heat pump coil was doing nothing. It was all on 10 kilowatts backup heat.
I think, too, it's interesting, Bill, because how many square feet is your house? Like 3,000, 4,000?
It's about 3,000 above ground, 1,600 on a conditioned basis.
Yeah, so 4,600 square foot, you're heating with 2 tons. It's got to run right because you sized it so it's got a really narrow band. Bill's was interesting because it was multifaceted. One of it was installation problems. It had an issue with the flare fittings are not being done right and refrigerant leakage. When we had refrigerant leakage, we had poor performance on the heat pump. I also think it was some control configuration, if I remember right, keeping that heat on. But then you had to run with electric heat on for how many months before you got your new heat pump put in?
You came out the day after New Year's Day. Eternally grateful for you doing that, driving out during a holiday weekend. Really appreciate that. You were like my care concierge supreme. Thank you so much.
But it was Maryland had cookies.
She did, yes. It was like 1 month later that we had contracted with Portman Mechanical, Tim Portman, to come out and install the new equipment, which the manufacturer, the builder, covered everything, including the labor. So all we had to do is just put up with the inconvenience for a period of time.
That was a tax on the sun.
Yeah.
I brought this up a little bit when we were at Brian Orr's symposium, was that the two guys I know that probably had the most resources at their disposal, Nate and Bill, both had challenges with their heat pumps. I know all the effort Bill went through to get this quality installation. When he's saying he offered the tools, and he literally offered the guys thousands of dollars of tools.
Yeah.
Here's a battery-powered flare tool. Here's a blue vac gauge. Here's a true blue hose for you.
Yep.
Here's a electric bender, whatever it was. There's a lot of tools that Bill offered the guy just to use them to do the installation. And none of that was done. Part of the interesting thing, because when I was out there with Bill, as soon as I hooked up the gauges, I could smell the acid. When you work with refrigerant, it's got a little bit of a sweet smell. When you get an acidic smell from it, it's actually making hydrochloric or hydrofluoric acid. And so I told Bill, I said, well, he goes, well, what's the verdict? I'm like, you're going to have to replace it. And he's, no, I'm like, yeah. I said, let's call the manufacturer. I'm telling you, there's no way to clean it up. So we get on the phone with the manufacturer, and I'm like, hey, I just want to confirm the metering device is inside the condensing unit. There's no place to put a liquid line dryer on this thing to clean it up. If this thing's got acid in it, it'll run a while till it's dead. But if this is Bill's forever home, this needs to be replaced. The manufacturer said, sadly, yes, there is no cleanup procedure. Go ahead and replace it. You never know when it's going to fail. And it's a chemical plant now. It's not just a condensing unit we had to replace. It was the condensing unit, the line set, and the indoor coil. The entire system has a disease now, a disease of acid and chemicals. Unless you replace everything, you can't clean that stuff out to stop that chemical reaction.
And just for clarity, so people got this in their minds, it's a air source heat pump, 2-ton, ducted. So it's got an outdoor mini split type condenser, indoor coil sitting before the blower, after the blower, the heat strips. Just give you a visual on that.
And the science behind that acidification, how common is that? And what happens there? What leads to that?
It's super common if you don't do a proper evacuation, but the question becomes, what is a proper evacuation? In 1969 or 59, I can't remember, maybe 1959, Review of Vacuum for Service Engineers.
59, yep.
Yeah, and they're like, if you read that book, there's a quote in there, and I'm going to paraphrase it, but it says, a finishing vacuum of 100 microns is desirable with a decay of no more than 200 microns to make sure there is no moisture left in the system and that the system has good control of the subsequent head pressure. This is back in 1959. Today, a typical evacuation is at 1,000 microns, right? So 10 times higher than what we did in 1959. What's changed in the industry? First of all, we forgot how to do a proper evacuation. If you read that book, that's what rebirthed this whole process. And Dave Boyd from Appian was the first one to bring it to light. Appian came out with their TES 8 pump, and they're like, oh, it's the best pump ever. And everybody goes, it doesn't do any better than my regular pump. And they're like, oh, what the heck's going on? Dave's dad was in the industry. He found the book, Review of Vacuum for Service Engineers, and Dave read through it, and it's, oh, we need bigger hoses. And so they put 2 6-foot, half-inch hoses on their pump, which had a conduction speed of 8 CFM, and that solved the problem, and monumentally faster than anything that had been done in years. And then probably about 7 years ago, we took it a step further. I really, really dug into the Review of Vacuum for Service Engineers and figured out the optimal conduction speed. But then also designed some hoses that were engineered for vacuum, because everybody had been using repurposed refrigerant hoses. And the reason was because people thought you would evacuate then charge the same hoses. But if you did it with 1/2-inch or 3/4-inch hoses, you'd have more refrigerant in your hoses and in your system. So we had to evolve a little bit, better use of core tools, hoses, less permeability, and then we could get much deeper vacuums than we'd ever achieved before, what they could do in 1959, right? But with evacuation, it's not really about what micron level you can hit. It's about what moisture level you can hit. Evacuation is all about dehydration. And so once we're below like 1,500 microns, 99.9% of the load is moisture. What we're talking about is what's the dew point of that moisture. We really want to get it down to an equivalent dew point temperature of about -60 is ideal. That's what a filter dryer will do, which is about 100 microns at -60. And that'll make sure the system is really dry. And then also with a heat pump, when we talk about subsequent control of the head pressure, we want to make sure we don't have any non-condensables in, because in the heating mode, those will end up in the indoor coil, and those will cause high head pressure, but not give you, a lot of people associate high pressure with high temperature, but it's about the latent heat of conversion. It's turning that refrigerant back from a vapor to a liquid. And if we lose condensing space into our coil, we have higher pressure, we're transferring less energy because we're not condensing as much refrigerant from a vapor back to a liquid. So there's all these fallouts that happen with improper evacuation. So the key things are dehydration and removing the non-condensables.
And what's the impact of the decay test as well? Because I see everybody posting about the level they can get their vacuum down to.
Yep.
But nobody's posting the follow-on metric for their decay.
So when we came out with these giant hoses, that was the next problem was you could hit a target really easily. So you could hit 500 microns. But when you isolated it, there was still water in the system. You could pull down so fast that people would think you're freezing the water. What you're doing is your vacuum pump in your hose is exceeding the rate that the vapor pressure can build up. As the water is bonded to the tubing, it's going to create a vapor pressure. And as long as the pump and the hose can remove that vapor pressure faster than it can build up, we can hit a target like 500 microns. But then when we isolate it, the vapor pressure slowly builds up and you'll see you're still below, let's say 1,000 microns. Your vacuum is decaying or it's going from 500 back up to 1,000. So you pull it down again, you'll pull additional moisture out that'll decay even slower. So you have to make sure that once you hit your target, you give it enough time to do a dehydration. Now, that's only if the system wasn't properly assembled in the first place. If you're flowing nitrogen through and you're doing good practices, you're not letting atmosphere get into your tubing, you're not going to have this buildup of vapor pressure after the fact. It'll pull down and it'll flatline and you won't have any appreciable decay. You always have a small amount of decay, but you won't have any appreciable decay. But if your tubing's been open like during installation or they ran the line set and didn't cap it, that decay is going to be very substantial. And so you may have to evacuate for several minutes to several hours to get the moisture out. If things were done on a system like Bill's, I think the manufacturer had a required test pressure of 600 PSI. If the tubing was full of air and you were to compress that air with nitrogen up to 600 PSI, then any moisture in that air will actually fall out as a liquid and as droplets in the line set. And then now you have to, when you evacuate, you have to turn that liquid back to a vapor, which takes a tremendous amount of time because you got to convert it back. If you didn't sweep your line set and push all the air out before you pressure tested it, that's also going to cause moisture to fall out in the system and increase your evacuation time and erode your decay.
The lack of knowledge of that type of HVAC science is a little surprising to me. Currently, in the place that we're renting, our landlord had an electrician put in a mini split a couple weeks ago. And at least he used smart tools. He told me that he got the vacuum down below 200. But because I went and asked him about decay, he just gave me a blank look. And so that makes, being that there's going to be so many, millions more mini splits and other heat pumps installed across North America over the next couple of years, that seems like it could be the typical case where there's so many people that they're almost there with their understanding, with their tools, with their capabilities. I'm just trying to imagine how many systems are going to be out there that are going to have moisture in them, where it's going to lead to this long-term problem where we might have to scrap a lot of heat pumps.
A lot.
It's the stuff good nightmares are made of.
Yeah, well, the thing is, Ben, it's not our knowledge that's the problem. It's our education. If you go back, Bill and I have known each other for over 20 years now. Yeah. 2001, I think we met. So 23 years now. And I was in the field. I was working on stuff that was 70 to 700 tons. I did large commercial industrial work. I had never really measured airflow. I don't know that I'd ever measured decay in a vacuum. I know I had not charged. I charged by superheat and subcooling and knew that, but I used analog gauges, things like that. When Bill and I met, I was just exposed for the first time to digital tools and combustion. I'd never done a combustion analysis, never picked up a combustion analyzer. I'm 15 years in the field and I'm a supervisor for all the younger guys working on all the rooftop units, things like that. I'm a great mechanic, but I'm not a technician. I'm not using technology to solve problems. I'm using tools to solve every problem I have. I'm really good at using tools. When I finally had a chance to get in the classroom and teach, I'd go out and tell the kids, oh, yeah, they'd ask me a question. I'm like, oh, yeah, let me take you out and show you. I take them out and show them, and I find out I didn't know what the hell I was even talking about because it did exactly opposite of what I thought would happen People say, oh, can you freeze moisture in a vacuum? And I'm like, yeah, let me show you how to do that. And I'd like try and do it. And there's no way this moisture's freezing. I found out later what I was doing wrong and what was happening. But it was challenges like that. I'd call Bill up at least once or twice a week and tell him, did you know you could do this or that? Or did you know these tools would do this or that? Does Tesla even know what they have over here? On the other hand, Bill and I were like, I'd call Bill and I'm like, hey, these things don't calculate superheat right. And we figured out the Germans didn't include atmospheric pressure in their calculation to correct from PSIA to gauge. So it was like we're both learning along the way. I was so excited at that point, and I found out how little I knew for how experienced I was. I've spent my last 25 years trying to educate people and teach them the things I had to learn the hard way so they don't have to. But it is an uphill battle. I'm always on social media. I don't want to say defending my position, but I'm trying to people pop off and I'm like, listen, here's the way it is. Here's what's happening. Here's what I'm trying to show you.
You're pretty polite and professional, but you have to be persistent and also have patience because it just repeats and repeats and repeats.
Well, I taught high school students, so I have a lot of that for 12 years. But I just think it's interesting. We can only learn so much in our industry. We can only absorb so much. And we absorb the mechanical parts of what we do, but we don't really get all the technical elements. People don't realize this is a trade. It's a lifelong learning commitment. We should really call this a practice, like lawyers practice law or doctors practice medicine. We should be in the practice of HVAC because it is really a lifelong learning thing. You can learn the mechanics of it in a year or two, but you cannot learn the science and the intricacies behind it in a lifetime.